Hello everyone, thank you for joining our presentation. We'll be presenting on our term project that is the comparison of an LSTM and transformer encoder on the AG news text classification. So my name is Abdullah Hassan and I'll be presenting along with my colleagues Shabih Ahmad and Zain Shabbir. So let's just get into it. Before getting into the main body, I just want to go through the table of contents. We'll be going through our introduction and motivation for this project, looking at the data set and the pre-processing we applied, followed by the development of the model, the main results that we had, the ablation studies that we did. In the end, we'll discuss some failures that the models had, and then we'll close out the presentation. So the main question is, why do we need to compare an LSTM with a transformer encoder at all? Both of them are standard sequence classifiers, but they differ in fundamental ways. An LSTM is a recurrent neural network. It processes tokens one at a time and carries information forward from one token to another. Transformer encoder, on the other hand, uses self-attention, which means that each token is related to every other token in the sequence. The key part of the project is to fairly compare both of these and to compare their behavior, not just their accuracy. So that's why we created both of these from scratch, and we utilized several techniques that can help us have a fair evaluation in our experimental setup. So a little about the dataset. We use the AG News dataset, which is a standard four-class news topic classification benchmark. Each example is a short news item that is assigned to one of four categories: world, sports, business, or science and technology. We used one source for the dataset, that is the Hugging Face website, to avoid mixing our dataset with different sources and different versions. So we split the dataset into training, validation, and use the official dataset for testing, 90% train and 10% validation. And none of the test set was used in the training or validation sets to prevent any leakage while you were testing the dataset. On this slide, you can see the pre-processing pipeline that we implemented for both of the models. Both models received the same text so that we could keep it fair. Text was lowercase and then passed through a regular expression tokenizer. Each model had the vocabulary capped at 20,000 units, and we used reserved tokens such as pad and unknown so that the sequences could be equal and unknown vocabulary could be categorized. Sequences were truncated so that they had the same length for each input, or padded or truncated. Having this identical pipeline helped us to make the assumption that any input and all of the output would be completely dependent on the model architecture instead of the data pre-processing or the data itself. With that said, I'll hand over to Shabi to explain to you the model.
Thank you, Abdullah. Let's look at the two architectures. The first is the LSTM classifier, an embedding layer and a single layer bidirectional LSTM, masked mean pulling over the real tokens, dropout, and final linear classifier. The second is the transformer encoder classifier. It is an embedding layer with learned positional encoding, two encoding layers with four attention heads each, masked mean pooling, dropout, and a linear classifier. So crucially, both were trained from scratch. As the boxes on the slide show, the LSTM has about 2.83 million trainable parameters and the transformer about 2.97 million, roughly around a 5% difference, which the assignment considers is reasonably comparable. Most of those parameters actually live in the shared embedding table, so the encoders themselves are close in size. To keep the comparison clean, both models used identical settings. The Adam optimizer, a learning rate of 1 times 10 to the minus 3, 6 epochs, dropout of 0.2, batch size 64, and cross entropy loss, and all were run on CPU with seed 42. So discussing the main results, here are the headline numbers. On the held out test set, the LSTM reached 91.20% accuracy and the transformer encoder 91.25%. The picture is the same for macro F1, about 0.9118 versus 0.9126. So we report macro F1 in addition to accuracy because even though AG news is balanced, macro F1 weights every class equally and would expose any hidden class specific weakness. So the transformer encoder does have the best final metrics, but the lead is only about 0.0005 in accuracy. So our honest interpretation is that both models perform almost identically. The transformer is marginally ahead in this run, but this is not decisive architectural win. So discussing about the training and validation loss curves, the loss curves tell a more interesting story than the final numbers alone. Training loss keeps falling steadily across all six epochs for the both models, but the validation loss stops improving and begins to rise in the later epochs. That's the region circled on the graph. That divergence is a clear sign of overfitting by epoch 6. We also noticed that the LSTM reaches a strong validation accuracy slightly faster in the first epoch. The practical takeaway is that early stopping or stronger regularization would be the logical next improvement for both models. Now, so now breaking the errors down by class confirms where the difficulty lies. Sports is the easiest class for both models. It has very distinctive vocabulary. The persistent problem is the overlap between business and science and tech because so many stories about technology companies contain both market language and technical language. For the LSTM 177, business examples predicted as science and tech and 121 the other way. For the transformer, 200 business items went to science and tech and 93 came back. Together, that single class pair accounts for roughly 44% of all test errors for both models, and this pattern lines up exactly with the failure cases Zain will show you next. Zain, over to you for the deeper analysis.
Thanks, Shabih. Now we ran two evaluation studies, each changing one factor at a time. The first and the required one varied the amount of training data, like 25, 50, and 100%, to ask which model is more data efficient. Our hypothesis was that the LSTM model would be more stable with little data, while the transformer would be more benefit from the full data set. Everything else, the split, tokenizer, vocabulary, sequence length, and training budget, was held fixed. As you can see, the results supports that hypothesis. Like 25 and 50% of the data, the LSTM is slightly ahead. At 100%, the transformer encoder moves inferred. In other words, the transformer gained more from extra data, about 4.5 points versus the LSTM's 3.7. The difference are the modest, though, so we describe this as a trend rather than the universal proof. The second evaluation varied sequence length, like 128 versus 256 tokens, in counter to what you might expect. The longer length actually hurt both models. Like AG news items are shorter enough that 128 tokens already capture the full signal, and the extra length only adds computation and noise. So further moving, we have done failure analysis and we have examined that the misclassified example in detail, deliberately including the cases both models got wrong, cases only LSTM missed, and cases only the transformer missed. So the three themes emerge. First, surface cues can override the true section. An Olympic story labeled "World" was called "sports" by both models, and this is also a case where truncation may play a role. Second, business and science tech overlay heavily whenever a story involves a tech company, an IOP, or a chip delay. Example two, like as you can see, an Intel product delay story fooled both models. And at the third, very short science items give the models too little context, which is where two models diverge. The transformer overweighted business like wording on the T.RX, IBM items, while the LSTM stumbled on some science and world cases. So the model fails similarly on general ambiguous text, but each also has its own distinct error profile. So, in conclusion, to summarize, both models reach about 91.2% test accuracy. The transformer encoder is slightly better on the final metrics. The LSTM is stronger in low data setting, while the transformer benefits more from the full training set. Longer sequence did not help. The main error pattern is business versus science tech. Both models overfit by the final epoch. Our recommended next steps are early stopping, stronger regularization, and repeating the study across multiple seeds for more robust conclusions. So that's conclude our presentation. Thank you all for your attention on the behalf of Abdullah, Shabih, and myself. Thank you so much for listening. And if you do like our presentation, give it a like and have a nice day.